Hello and welcome to CO 738 Probabilistic Methods. Today we'll be discussing Brun, Sieve, and the Poisson paradigm. So what is the Poisson paradigm? Roughly it says that if X is the sum of many rare and mostly independent indicator random variables, and mu is the expectation of X, then we would like to say that X is close to a Poisson distribution with mean mu. So rare, that they happen infrequently, and mostly independent in the sense of our last lecture. In particular, this would give you that the probability of X equals 0 is nearly e to the minus mu, and that more generally the probability that X equals t is nearly mu to the t over t factorial times e to the minus mu for any integer t greater than or equal to 0, as that is what the Poisson distribution would give you. So that is the Poisson paradigm, but again, we would like to say, so we need conditions under which this formalization is allowed. And that's what we'll be talking about today. So Janson's inequality offers one approach to this. We saw where probability X equals 0 was indeed nearly e to the minus mu, this expectation of X, where X was the sum of these rare and mostly independent indicator random variables in a certain setting. Now another approach, the more traditional approach, was developed by the number theorist T. Bruin in 1915, and we'll start with discussing that. So what is Brun's sieve? Well, let B1 up to Bm be events, and xi be the indicator random variable for Bi. So somewhat similar to Janson's, but here we're not assuming anything about the probability space, really. And then we'll let x be the sum of these xi, i.e. it's the number of events that occur. And then the key is that n will be a hidden parameter. So in fact, this setup, we're not thinking of it as one probability space or random variable, but many. So the number of events m will depend on n, so will the bi's depend on n, and the x's as well. So we think of them all as a function of this n. Then we'll define s to the r as being the sum over s and m choose r, so any set of r of the m events, of the probability of the intersection of the bi, where I is in S. So we think of all the possible r tuples of events and the probability that that r tuple happens. And then we're going to write x to the r as kind of a falling factorial here of x minus 1 down to x minus r plus 1, product of all of those. And the inclusion-exclusion principle actually yields that the probability that x is equal to 0 is equal to the probability that the intersection of I and m of bi not happening, so that is actually equal to 1 minus s1 plus s2 alternating, so the general term being a minus 1 to the r, sr. So that you get from inclusion-exclusion. So now that we have that set up, let me tell you the theorem. So the theorem is, suppose there is a constant mu such that e of x, this expectation, which is of course s1, goes to this constant mu. And what is goes to the right arrow, meaning as n goes to infinity. And then also further suppose that for every fixed r, the expectation of x choose r, so really these are these higher moments, right? So x choose r you could write in terms of the moments up to the rth moment, which is this SR, would go to mu to the r over r factorial. So why is that nice? Well, those are the numbers that you would get if it operated like a Poisson distribution. And now the claim is that actually these probabilities also converge. So probability of x equals 0 would go to e to the minus mu, and for every t, the probability of x equals t goes to mu to the t over t factorial, e to the minus mu. So essentially what are we saying with this dependence on n? If you can promise me all the moments act like they would, so you're really getting these mu to the r over r factorial, then actually we can guarantee that these probabilities converge as if it's the Poisson distribution. So to mu to the t over t factorial, e to the minus mu. So we're going to go ahead and prove this theorem, but I'm only going to do the case t equals 0 for simplicity, as the other ones are a bit harder. So how does this work for t equals 0? Let's fix epsilon greater than 0. So that'll be our wiggle room kind of for the convergence purposes. And we're going to choose s such that if we sum up this minus 1 to the r, mu to the r over r factorial, if we sum up all those minus e to the minus mu, that will be at most epsilon over 2. Right, so those are somehow the first 2s or 2s plus 1 terms of e to the minus mu. And so we're going to choose this s, right? So we know that such an s really exists, right? So e to the minus mu has its Taylor expansion, so there's some s that will get us within this approximation. So get us that if we take enough terms, we can get within an epsilon over 2 factor. And now we're almost done. So the Bonferroni inequalities state that in general, the inclusion-exclusion formula overestimates the probability of x equals 0 for even r, and then underestimates the probability x equals 0 for odd r, right? So you start out with 1 and then so on. So the Bonferroni inequalities, if you don't know, really they're just generalization of the union bound. They're really kind of what the inclusion-exclusion formula as thought of today, but you might not have known that actually they do this over and underestimating, which you could prove with a bit of enumeration or induction, but let us not do that. So why can we use this? Well, now, in particular, this implies the probability x equals 0 if we take the first 2s term, 2s plus 1 there with it ending in even, that gives you an upper bound. So then it's at most r equals 0 to 2s of minus 1 to the rs, minus 1 to the r of sr. And now we're basically done because we just select an n0 such that for every n at least n0 and r in 0 to 2s, that sr minus mu to the r over r factorial is small, right? So we were promised that sr converges to this mu to the r over r factorial. And so for each one, we can just take, there's an n for which we can be below this. We'll take the max of all those. And so we'll get this epsilon over 2, 2s plus 1, as there's 2s plus 1 terms. So essentially, each one has an error of that, so all of their error together is only epsilon over 2, and then the other part from those terms to e to the minus mu, those sums, were also only an epsilon over 2 error, so altogether this shows that for such n, the probability that x equals 0 is at most e to the minus mu plus epsilon. And then you just do the same for the other sum, right? So we take the sum out to 2s plus 1, so it's odd, and then that means that we can lower bound it appropriately, and then once more we can, now we'll do 2s plus 2 terms, but we will find an n1, where for every n at least n1, they're small again, they're close, and it'll all add up, and you get an epsilon over 2 and another epsilon over 2, but this time below, so the probability x equals 0 will be at least e to the minus mu minus epsilon. And so indeed, as epsilon was arbitrary, this shows that the probability x equals 0 converges to e to the minus mu, concluding the proof. So that's all it really was saying, is we can use, if we control the moments, we can use the Taylor expansion of e to the minus mu and approximate that as well as we want, with somehow just a finite number of these terms. And we could use this type of technique to more generally do it for any fixed calculation there. For probability x equals t, you can imagine how that go, but we will not do that. So now I want to move on and in the rest of the lecture try to give you a sense of how to apply Brun's Sieve, the Poisson paradigm, and some of Janson's inequality. And we may do more with Janson's in applying it, but let me recall for you what Janson said, as we will also need it here. So what did Janson say? You had a set of events bi, you wanted to bound the probability none of them happened. You define delta, this pairwise independence. You define m, which is the product of them not happening, and then mu as before, this expected number of events. And if they were all rare, so if the probability of the bi's was at most epsilon for every I, we knew that the probability none of them happened was at least their product, and at most the product times this e to the 1 over 1 minus epsilon delta over 2. And furthermore, we could also upper bound it with this e to the minus mu plus delta over 2. So what does that say? That somehow if delta is small, like little o of 1, then really this probability is approximately m is approximately e to the minus mu, so it is close. And we did the extended Yanson's inequality, which we won't use today, but I'll just remind you, if delta is the least mu, then you can get also a useful value of e to the minus mu squared over 2 delta. So I wanted to mention one more generalization, which is how does Yanson's inequality connect to the Poisson paradigm? So I mentioned it's kind of an approach. So you might want to pause the video and think, again, how does Yanson's connect up with the Brun Sieve with this Poisson paradigm? Well, for one, Yanson's can be used to prove that the probability x equals 0 is approximately e to the minus u. So if x happens to be from this certain probability space that Yanson's applied to, we can indeed use it to do that that first part. So if that's what we really care about with the Poisson paradigm, it's just the x equals 0 case, that will be covered under the more stringent conditions of Yanson's. Now, also, however, it can sometimes, as you'll see in this lecture, be used to show the more general probability x equals t statement as well. So sometimes we can also include that from Yanson's. And now, what else can we do there? Well, Yanson also proved a tail version as follows. So you may be interested in this, is that if the assumptions of Yanson's hold and mu is equal to e of x, so again, define x to be this sum of the indicated random variables, and gamma is any arbitrary number greater than 0, then the probability that x is multiplicatively smaller, so is 1 minus gamma times mu, is at most e to the minus gamma squared mu squared over 2 mu plus delta. So it gives you a certain tail probability there. And I'll note when delta is equal to little o of mu, this really approximates that of a normal curve with mean and standard deviation mu. And this should also be nice in comparison to things like Chernoff's or Talleyrand's, right? Because there, this gamma mu is that difference, that t from the expectation. So you're getting a t squared up top, and something like some constant times the expectation, but plus some other number there. And so it's actually quite nice there if delta is small. But this also goes back to giving you numbers even when the extended Yanson's, when delta is large, it still applies, as gamma would be 1. So it is quite nice that it works even if you want to do not x equals 0, but smaller values, right? So in particular, somehow the x equals t case, it would also give you some insight into that. So that's all I wanted to say about extending Yanson's. On to our applications for the day. So here's kind of the first, a very basic application of Yanson's that maybe shows you some of its power. And so here's the question. What is the threshold function for the property that GNP is triangle free? So you may remember we kind of talked about this, so I'll let you pause the video and think of an answer. Do you remember what this answer would be? So if you're back, well, a triangle, if you remember, we talked about this during the second moment method, is what we call balanced, right? And so the threshold functions is, as previously shown, it's n to the minus v over e, which is n to the minus, that's vertices over edges. There's 3 vertices, 3 edges, so you get n minus 3 over 3, which is 1 over n. So we had done that before, right? You can go one direction using first moment method, so Markov's inequality, and then the other direction we used Chebyshev's, i.e. the second moment method, to show that. Now, with our greater expertise, we could actually, instead of Chebyshev's in the second moment method, we could actually use more advanced concentration inequalities such as Talleyrand's to also show this, but nevertheless, that is the threshold. So we've already covered this, so why am I asking? Well, now we can ask a deeper question. Namely, what is the probability GNP is triangle free near this threshold? Right, so we know the thresholds, right? So threshold was if you're much smaller than 1 over n, it would be triangle free, much larger would not be, but somehow we don't have a good understanding yet of what the behavior is around the threshold, from 1 over n, 2 over n, 10 over n, etc. And the idea is that actually in the limit there will be some probability. So more formally, we'll let p be c over n for some constant c. And we're asking, really, what is this limit as n goes to infinity of the probability that GNP is triangle free? So what will that number, so the idea is that this number will exist to be a very specific number, depending, of course, on c, and that will actually kind of show that as c goes to infinity, it'll go to 0. As c goes to 0, it'll go to 1, showing that it is indeed the threshold. So this is quite nice, giving a finer picture of the threshold. So this is, again, just an example which we could do with many other threshold problems, but we'll apply Jansons to do it. So here's the answer. If p equals c over n for some constant c, then this limit will be, I claim, e to the minus c cubed over 6. So it's some magical function of c there. So where is this coming from? Well, let's go through it. We're going to we're going to apply Janson's inequality, as promised, as follows. So how do we do this? Well, for S, a triple, so n choose 3 there, we'll let BS be the event that GS is a triangle. So that triple forms a triangle. And we'll note that the probability of BS is, of course, b cubed, and that number is c cubed, gives you c cubed, we have the c over n, so it should be c cubed, sorry, that's a typo, that would be c cubed over n cubed, which is little o of 1. And then we can use linearity of expectation to say that mu is the sum of these, the probability of these s's, which is n choose 3 p cubed, which would give you, n cubed over 6 times c cubed over n, which is c cubed over 6. So sorry for the typo before, but we get this c cubed over 6. So the actual expected number of triangles is some constant depending on c. And that's what somehow maybe allowed us to apply Markovs and such, but now we want to go from there. So what good is it? We know the probability of BS, we know the expectation, mu here. Well, now we just calculate the rest, right? So triangle free means that none of these events happen. So we want to avoid these. So we calculate it as if they were independent. So m, our product of the non-events, the probability of non-events. So what is the probability of BS complement? Well, BS was p cubed, so we get 1 minus p cubed. There's n choose, they're in, we're just taking a product, so there are n choose 3 such events. So we get, that's approximately e to the minus n choose 3 p cubed. P cubed is quite small, which will give us from above is approximately e to the minus c cubed over 6, which is that number above. So maybe now you see, using Jansons, we would hope it'd be m, which should, if Jansons applies, be approximately e to the minus mu, and that c cubed over 6 is this mu, as it turns out, in the limit. So now we're almost done. We have mu, we have m, we have to look at delta. So what is the dependence? What is the number of triples s and t where s, tilde is t, so where they overlap? Well, so that means they have to share an edge in common. So that means that I get n choose 4 there. So I have to look at 4 tuples, and then I choose the edge where they're going to overlap. There's 6 choices, which again, it doesn't really matter about the constants. It's on the order of n to the 4th. And now for each such pair, the probability that BS and BT both happen, so that both of them are triangles, well, they have 5 edges, right? So they have an edge in common, and they each have 2, so that's going to be a p to the 5th for the probability there. And this should be reminiscent of those second moment method type calculations we did, where we calculated similar deltas. And thus delta is the sum is O of n to the 4th times p to the 5th, which, since p is c over n, is little o of 1. And now we're done, because by Janson's inequality, the probability that none of these happen goes to m, because again delta is little o from the mu there, and so mu was some constant, so you go e to the minus c cubed over 6 as desired. So that was quite nice, is that actually Janson's inequality can do a bit more than on the threshold functions than just applying Markov or applying the second moment method. And really, it can impactfully reproves them, right? Because as c goes to infinity, that would go to 0. As c goes to 0, that would go to 1. So it really is showing the threshold there. And so somehow Janson's is incorporating both the first moment method and the second moment method in this. And I won't go through it, but the same proof would adapt to show that a strictly balanced graph, so remember, a balanced was your node denser, somehow this v over e than subgraphs, and then that you're as dense as those, and the strictly balanced being that you are strictly more than. And so what this can be adapted to show is that a strictly balanced graph H with A automorphisms, and P being C, some constant there, times n minus V over E, So n minus v over e, remember, would be that threshold function. So satisfies that the limit that GNP is h-free is equal to e to the minus c to the e, where e is not e, 2.7, whatever, is number of edges, instead divided by a, the number of automorphisms. So for triangles, it had 3 edges, so you get a c cubed, and it had 6 automorphisms, so you get a 6 on the bottom. And why is that? Well, essentially the proof is the same. You get the number of automorphisms there when you're calculating the expectations and such, and then you get, you end up with the number of edges because you're getting, p to the e and such. So then what does that give you? Well, the proof is a little bit harder because you basically the mu, the m, that all works the same. The issue is, the delta thing is a bit more complicated, but if you remember our calculations for the second moment method, it's essentially the same, but we have to use, strictly balanced, and then that will show that delta is little o of 1, and so you could apply Janson's. So I won't go through all that. You can check along in Spencer to see more details, but that's also quite nice. So really, these statements we had before when discussing the second moment method that we can really get tight control all now follow from Janson's. For one last application of today, I'm going to do something a bit harder. So something that will actually use both Janson's and Brun's sieve. So let epit, or EPIT, which is every point in triangle for short, be the property that every vertex is in a triangle. So why did I call it epit? Well, I went with epit, as they had. So what is every vertex is in a triangle? What am I going to ask? This is a property, so what is the threshold function for EPIT, right? So the monotone property, so what is its threshold function? And now this seems a lot harder to answer. We haven't done something like this before. So I won't make you pause and stop the video and think of the answer, as it's not really clear a priori what this answer should be. So I'll just tell you a theorem that answers it. So let c greater than 0 be fixed, and let p equal pn, mu equal mu of n, satisfy n minus 1 choose 2 of p cubed equal mu, and e to the minus mu equal c over n. So that's a bit random, but I'm somehow setting up mu to be some expectation there, and p to be some appropriately chosen probability for this various c. And what I'm going to claim is then the probability in the limit that GNP satisfies epit is equal to e to the minus c. And so somehow whatever threshold function we have here, that this is giving it, right? Because as c goes to 0 or c goes to infinity, it's giving you the right numbers there. Okay, so now let's go through that. How does this work out? Well, the threshold function for ipit, then, if you work out the details, so if you solve for mu, you'll end up with n to the minus 2/3 times a log to the n to the 1/3, if I didn't do the arithmetic wrong there. And mu would be approximately log n over c. So you can solve that, and then you can solve for what p should be, and set c to be, say, 1, because you don't really care, as you're just trying to find the general threshold, and so that gives you that. So that's a bit weird, right? So it's a bit weird of a threshold function with this extra log term. We haven't really seen that before. But anyway, it'll follow from those calculations, and it follows from this theorem. So now how do we prove this theorem, right? So that's a good question. Well, again, a nice combination of Janson's and Brun's sieve. So let's look at the proof. So fix a vertex x of the vertices of G, and let's go through some things. So for each unordered y and z in V of G minus x, we'll let bxyz be the event that gxyz induces a triangle, right? So we want every vertex to be in a triangle, so we look at first vertex and ask, like, what's the probability that that vertex is actually in a triangle? So we look at these different events. We'll let cx be the intersection that the complements of the bxyz, which is therefore the event that x is not in a triangle. So what it means not to be in a triangle is that none of those events happen, and we'll let xx be the corresponding indicator random variable. So somehow we have to figure out what the probability here is of these cx's to really get a grasp on what the threshold should be. And the claim is that the expectation of xx, which is the probability of cx, of course, is actually approximately e to the minus mu. So it goes to that, which is then c over n. So that's the hope that we want to prove this, right? So c over n by definition of mu. So how are we going to do this? So how do we prove that this probability of cx is so tightly concentrated? Well, it should remind you of Poisson paradigm, but actually we'll use Janson's here, since we just want to show that none of these events happen, right? So we're going to show none of events happen. We want to show as if they're approximately independent, so we use Janson's. So proof, we use Janson's. All right, so let's go ahead and do this. You might want to go ahead and pause the video yourself, work through the details. This is a good exercise. Janson's, you just have to figure out the right parameters and make sure they check and work out. But we'll do it for you. So probability of one of these events, these b, x, y, z, it's always the same. It's p cubed, which is little o of 1, of course. So that means they're rare. So I don't have to worry about that epsilon consideration. Meanwhile, mu, the sum of these probabilities is there's n minus 1 choose 2 choices for y and z, so you get n minus 1 choose 2 p cubed, which luckily is exactly as we defined it in the theorem, so I don't have to give a new mu, I just can use the old one. And now we're almost done, so for dependency, bxyz and bxy prime z prime, they're tilde, they're dependent. Well, if and only if yz and y prime z prime intersect, right? So we don't care about the intersecting of x, of course everything intersects in x. Rather, they have to overlap in an edge, so one of the other two must be equal. And so hence we can write this delta as a sum over y, z, and z prime, the probability bxyz intersect bxyz prime. So we could just assume, say, the y's are equal by renaming. And what is that? Well, then if you go through, so we have to choose a y, a z prime, so this n cubed choice is roughly there. And again, we need we need two triangles overlapping the edge, so that's p to the fifth. And importantly, that's little o of 1, since p, was actually more like n to the minus 2/3, which is little o of n to the minus 3/5. So sure, it had a log term, but it's still little o, so that's good enough. And now we're done, because then by Janson's inequality, the probability of the cx is approximately e to the minus mu, as delta is much, much smaller than mu, and so that will be c over n by definition. Okay, so that concludes our first claim, the proof of that claim, where we got a handle on the probability of one individual vertex being, somehow in a triangle, not in a triangle, right? So now let's continue on. So we had the probability where it's, not in any triangle being this c over n for this appropriate choice of b. So now we define x to be the sum of these indicator random variables, the xx, which of course would be the number of vertices not lying in a triangle. So it's a bit weird. This is all a bit backward than how you might think to do it about, well, let's count up the vertices, in triangles. But the idea is we want to, again, apply this Poisson type paradigm. So we want to get some control when x is something fixed. So it actually makes more sense to not, right? We want every vertex to be in a triangle. So we want to set every vertex being a triangle somehow being some x equals 0, so you do the not, right? How many vertices are not in a triangle? We want that number to be 0 using this Poisson paradigm, Brun, Sieve, Yanson's, etc. So it's a bit inverted than what you might think, but it really works nicely. And now we're almost done. We're by linearity of expectation, e of x is the sum of these e of the ex. There's n vertices. The expectations were c over n, so that just goes to the nice constant c. So that's somehow the nice choice of all this setup is the expected number of vertices not lying in a triangle is just some constant c, so we'll be able to get a handle on it. And we want to apply the Poisson paradigm to x to do these probabilities more directly. And so how can we do that? Well, we fix an r, right? So we understand the expectation of x. We actually have to do it for all of the x choose r, all of the r tuples. So then the expectation of x choose r, which is this s to the r, is the sum over r tuples, n choose r there, of the intersection of these cx's, where x is an s. And remember, cx, so that x is not in a triangle. So somehow I have to sum up all of these joint probabilities that vertices aren't in triangles. Well, a nice observation is that all R sets look alike, right? So the expectation of XR is really, we can just focus on one. We can say it's n choose R times the probability that this particular one, that none of them are in a triangle. which will be approximately, if we approximate the binomial coefficient there, is n to the r over r factorial times this probability. And now the key then is we just have to get a handle on what this probability is, right? And you might think, how are we going to do that, right? How are we going to get a handle on that? We did this before with one cx, but how are we going to handle on the intersection of all of these? Well, the key is it's really the same, right? We still can use Jansons, because the intersection of these cxi will be the intersection of iyz for bxiyz, right? So all of those triangles not happening. So really all of these are just more events we're adding in to not happen, but it's still something we can get a handle on. So we apply Jansons to bound this probability as well. So isn't this glorious, right? We're going to use Bruin Sieve, we're using Jansons twice. So one in the base kind of case of e of x for one cx there, and now more generally when we have r of them. And we can still do this, right? So we just have to count up the number of these pairs. So there's that number of xi, y, z is, well, what is it? So for each one, there's r choices for I, there's n minus 1 choose 2 for the rest, except you kind of have some possible overlaps of triangles. But the claim is that these overlaps are only O of n, so you get minus O of n. And why is this? So you might want to pause and think for a moment. Do you agree with this statement? Well, the overlap is only order n, is only linear because r is a fixed constant, right? So it's very important here that in this Poisson paradigm, that for our application, that r is, we only need to do this when r is some fixed constant, not depending on n. Because otherwise then the overlaps could be a lot more. But here, again, they're somehow only linear, right? You choose a pair of them, that's r choose 2 times something like, n minus 2, it's only linear. All right. So now that we have that, we know that then the sum of the probabilities of these BI, I'm sorry, that's, a typo there. It shouldn't be the complement. It should just be of the BXIYZ is P cubed. So we're trying to find this, somehow this new mu, which is P cubed times the number of events, right? So for each one probability triangle is P cubed, you get R n minus 1 choose 2 minus O of n equals R mu. And it's linear, so really that's times 1 plus little o of 1. So again, sorry about the typo there with the overline on the B. And now we're really almost done. So there's the finish of the proof. We've calculated our new mu for an R tuple. It's roughly R mu, which is great. And as before, delta would be P to the 5th, so probability to get these two overlapping triangles, times the number of pairs xi, yz, approximate, sim, xj, y prime, z prime. And so what is that? Well, there are r times n cubed terms when I is equal to j, and r is a constant, so that's on the order of n cubed. And there's r squared times n squared terms when I is not equal to j. So that's on the order of n squared terms. So you'd end up choosing, again, a pair of them and then taking those triangles. But again, so really they're dominated by the first term, the second term is O over n squared. Altogether, we get at most that delta is O of n cubed P to the 5th, which P again is little o of n to the minus 3/5. So that's little o of 1 again, as before. So really, the point is we can apply Jansons. So by Jansons, the probability that none of these R tuple is in a triangle is approximately e to the expectation minus expectation, which is e to the minus R mu. And now, we're almost done, because then if we go back and plug that into our expectation of x choose r, we had an n to the r over r factorial times this probability. So we can rewrite that as n e to the minus mu all to the r over r factorial, right? So we can bring that e to the minus r, e to the minus mu under the r. And now you should recognize that we set up e to the minus mu to be c over n, so you just get actually equal to c to the r over r factorial. And then why is that good? Well, then we're done by Brun's sieve, right? So we had this probability of, x being 0 would be go to e to the minus e of x. Remember, e of x was just c, and more generally, we showed e of x choose r was c to the r of r factorial. So then Brun's sieve guarantees you that the probability that x equals 0 goes to the expectation, e to the minus expectation of x, which is e to the minus c, which is what we claimed. And therefore really establishes that this is also the threshold function, while additionally giving us insight into the probabilities near that. So that's all for today, where we showed off the Poisson paradigm, showing that the probability x equals 0, or more generally x equals t, is what it would be in a Poisson distribution under certain circumstances, as in Janson's, but also with this Brun sieve. So if you can control all fixed finite moments, then we can also get there. We used Janson's to discuss actual probabilities near the thresholds for subgraphs, in particular for triangles. And then more generally, properties like this, where every vertex is in a triangle, which seems strange and has a weird threshold, but we used a combination of Brun sieve and then really Janson to do the legwork of showing that the properties of Brun sieve hold, to end up showing again that where the threshold is and an exact probability for that. So that's all for today. Until next time, see you then.